Hello, welcome to another module in this massive open online course. So, we are looking at various aspects of source coding, the fundamental bound on the lowest possible average length of the source code for a given source, and also we have seen the mechanism by which we can approach this lower bound, that is by coding symbols across larger and larger block lengths. Alright. So, in this module we will look at a practical scheme or an algorithm to construct an efficient source code for a given source, which is a very simple and elegant scheme termed as the Huffman code. Okay. So, that is the algorithm we will look at in this module. So, we would like to understand more about the Huffman code, which is a very popular and efficient code or an algorithm to construct. It is not a code, it is a very popular algorithm to construct an efficient. So, it is a very popular and simple algorithm to construct a prefix free code. For a given source with a source alphabet and a certain probability distribution. With a certain probability distribution for the source, with a certain probability distribution for the source alphabet. Okay. And the Huffman code is the optimal code in the sense that it yields the code with the shortest average length, with the smallest average length for a source with corresponding to that particular probability distribution. Okay. So, the Huffman code is very efficient. Okay. It is a very efficient code. Or rather a mechanism to construct a very efficient code and yields the code with the shortest, this can be shown that it yields the code yields the code with the shortest average length. In that sense, it is the optimal code. Okay. So, it yields the code with the shortest average length. In that sense, it is the optimal code, and we will illustrate this with the aid of an example. So, let us illustrate this with the aid of an example. Let us describe this with an aid of an example. Consider x, symbols x drawn from a source with alphabet S0, S1, S2, S3, S4, and the probabilities are the probability of S naught equals 0.15, the probability of S1 equals 0.2, probability of S2 equals 0.15, probability of S3 equals 0.25, and probability S4 equals 0.25. And you can see that even before we start, this is a valid probability distribution, because sum of all probabilities, the sum of all probabilities is equal to 1. Okay. Now to start with, so what we want to do is basically we want to construct the optimal code, that is the Huffman code. That is, we want to illustrate the procedure to construct the Huffman code for this source with this source alphabet and the probability distribution that is given. Okay, so that is what we want to illustrate. Okay, all right, and so we are interested in to construct the Huffman code for this source. To construct the Huffman code for the given source. Now the first step that is, if I were to write this in steps for clarity, list symbols in decreasing order of list symbols in decreasing order of probability. List the symbols in decreasing order of probability. So you can see that the probabilities are 0.5, 0.15, 0.2. So if I were to list the symbols in decreasing order of probability, I can arrange them as, well, S3 and S4, which have probabilities. Let me write that as much to the left as possible, as you are going to see shortly that we are going to keep progressing towards the right. So S1, S1, S2, S0. So this is 0.25, S4 probability 0.25, S1 probability 0.2, S2 which has the next lower probability. Of course, S2 and S0 have the lower probabilities, which are 0.15 each. Okay. Now what we do is we fuse or combine two symbols with the lowest probabilities. Now if you look at this, S2 and S0 have the lowest probabilities. Okay, these have the lowest probabilities. So in the next step, so these are the lowest probabilities. So therefore what we do is we fuse, or basically we combine these. Okay, so we combine this, we fuse these two, assign a 0 to one branch, let us say the top branch, 1 to one branch, the net probability becomes 0.3. Okay, and so we fuse or combine these two symbols and add their probability. So we are taking the lowest probability symbols, fuse or basically combine them and add their probabilities. So in step number 2, what we are doing in step number 2 is we take the symbols, fuse, combine, or fuse the two symbols with the lowest probabilities. And we add their probabilities. That is the most important thing. We add their corresponding probabilities. So we are fusing these two symbols which have the lowest probabilities, and then we are correspondingly adding their corresponding probabilities. Okay. And so to one of the branches we are assigning 0, to the other branch we are assigning a 1, and the significance of that you are going to see slightly later. Now what we do, so we are assigning a 0 to one branch, assign a 1 to another branch. So we assign 0 or 1 to the two branches, and now what we do, now we have these two. So we have the original symbols S3, S4, S1, and this fused symbol which is S2 and S1. Now we repeat the same step. Now we go to step 1, these resulting symbols. So now you have to look at the effective symbol set that we have. We have the unfused symbols S3, S4, S1, that is unfused symbols at stage 1, okay, and the fused symbols, that is S2 and S0. Now again reorder their probabilities, fuse the symbols with the lowest probabilities. To the branches, assign 0 to one branch, 1 to another branch. Proceed until all the symbols are fused into one effective symbol. And naturally when you fuse all the symbols, since you are adding their probabilities, the total probability of the net fused symbol remaining in the end will be 1. That is when we stop the scheme. Okay. So now step number 4, we reorder the probabilities. This is very simple. Reorder the probabilities and start from step 2. So you reorder the probabilities, start from step number 2, that is by fusing the probabilities corresponding, fusing the symbols with the lowest probabilities and adding their corresponding probabilities. Now if you look at this stage, in this stage the probabilities that we have are 0.25, 0.25, 0.2 and the fused symbol with 0.3. Now naturally this fused symbol with probability 0.3 will go to the top because it now has the highest probability by virtue of the addition of probability. So that will go to the top, okay. So that will go here, that will be 0.3 and the rest of the symbols for instance will come down when you order them. So S, after that you have S3, after that you have S4, finally you have S1 which is 0.2. Now the lowest probability symbols are, well, they are S1 with probability 0.2 and S4 with probability 0.25. Well, you can either choose S4 or S3, does not matter, both have probability 0.25. So now you fuse, well, now you fuse S1 and S4, assign 0 to one branch, 1 to another branch, it becomes 0.55, 0.45 the net probability. So that again when you reorder it goes to the top. So this is 0.45, okay, and then you have 0.3 which will be the next one, and then you will have 0.25 which is S3. Now the lowest probabilities are S3 and S. The lowest probabilities are 0.3, which corresponds to, remember, the fused symbol S2 and S0, and of course S3 with 0.25. So now you fuse these two, 0.3 and 0.25, assign 1 to one branch, 0 to one branch, 1 to another branch. This becomes 0.55. You have 0.45, which is another fused symbol, and now when you fuse it becomes, and again you assign 0 to one branch, 1 to another branch, and then you get the effective fused symbol. This completes the algorithm. So this is where all symbols fused with all symbols combined. So the probability of that, since we are adding all the probabilities, in the final stage we will get a fusion of all the symbols, correct, and the probability of that will be 1. Alright, since we are adding all the since we are fusing, we are adding all the probabilities. Okay. Now, so now that completes the process of constructing this Huffman tree. So this has completed, if you can see the tree, and now to find the code you backtrack along the tree. So to find the code, backtrack along the tree. Backtrack along tree to each alphabet or each symbol, correct. You backtrack along the tree to each symbol. For instance, to find the code corresponding to, let us say, symbol S0, well, S0 will be S0, remember S0 is going through 1 and then it is going through the top to 0.3, finally 0.3, the branch 0.3 is assigned 0 here, and finally it is going into 0.55, which is assigned another 0. So the code for S0, so the code for S0 will be, the code for S0 will be 0, 0, 1. That is, if you backtrack this, find the path to, so you start with 0, 0, 1. So S0 corresponds to 0, 0, 1. Let me repeat this procedure again. If you trace the path from S0 to this root node, you can see you start with S0, the corresponding branch has 1, okay. Then you, the fusion results in probability 0.3, 0.3 goes over here. Now in this stage where you are fusing 0.3 and 0.25, 0.3 is assigned 0, again it goes into 0.55, and in this stage finally when you are fusing 0.55 and 0.45, 0.55 is assigned 0. So now if you backtrack along this path to the path of 0, what you will have is 0, 0, 1. Similarly, if you backtrack along the path to path S2, S2 will be 0, 0, 0. So basically by backtracking, like looking at the path and looking at the bits on the path, that eventually leads to it. So what we are doing is we are backtracking, starting from this effective fuse symbol which is probability 1, we are backtracking the symbol to backtracking the route or backtracking the path along this tree, this Huffman tree, to each symbol, and along the way we are collecting all the bits that we are observing on the various branches, and that basically forms the code word for that particular symbol. I have to describe it in very simple terms. It is basically the sequence of bits along the path starting from this effective towards fused symbol towards each of these symbols in the alphabet. Alright, so we have seen S0 is 0, 0, 1, S2 is 0, 0, 0, and you can similarly formulate the list. So the final code, Huffman code, will be the Huffman code that has been finally designed is basically for S0 we have 0 0 1, for S1 we have 2 bits 1 1. You can find this from the tree. For S2 we have already seen we have 0 0 0, okay. S3 we have 0 1, and S4 is represented using the 2 bits 1 0, okay. And you can observe, so this is basically your Huffman code, okay. And you can observe that the two lowest probabilities, one interesting thing which is the property of the Huffman code which is always true, is that the two symbols lowest probability symbols have code word lowest probability symbols have code words of equal length, okay. So the lowest probability symbols have code words of equal length, okay. So that's an interesting property of the Huffman code. The lowest probability, two symbols with the lowest probabilities have equal lengths, okay. And now what we are going to do is let us compute the average code length for this code word for the Huffman. Now before that, let us first verify that this is a prefix free code, and we know how to verify that this is a prefix free code. So we want to, of course, so let us check that this is a prefix free code. So we have S0. So let us say 0 represents the top branch. Remember, we can always verify a prefix free code using the binary tree representation. So 0 0 0, that gives S0, 0 0, I am sorry, 0 0 1 gives S0. So 0 0 0 gives S2, 0 0 1 gives S0, 0 1, this gives S3, and 1 0, this gives S4, and 1 1 gives S1. So this is a binary tree representation for the code that we have constructed. And observe from this binary tree that no code word or no symbol is an ancestor. No symbol is an ancestor of any other symbol, that is no symbol lies along no symbol lies along the path to another symbol in this binary code tree, which implies this is a prefix free code or an instantaneous code. Which implies this is a prefix free code, okay. And we would like to calculate now what is the average code length. To calculate the average code length, let us write this table. So we would like to calculate what is the average code length. So to calculate the average code length, let us start with a table. So this is your symbol S0, S1, S2, S3, S4, and the code corresponding code is S0 is 0 0 1, S1 is 1 1, S2 is 0 0 0, S3 is 0 1, and S4 is 1 0, and which means the length, that is also obvious, S0 is length 3 bits, S1 is length 2 bits, S2 has length 3 bits, S3 has length 2 bits, S4 has length 2 bits. And finally, let us write the probability of each. We know what are the probabilities of these different code words. What are the probabilities? Okay, so the probability of S0 is 0.15, probability of S1 is 0.2, probability of S2 is 0.15, S3 and S4 have probabilities 0.25 each. So therefore, average length equals summation I equal to 0 to m minus 1 pi li, which in this case would be 3 into 0.15 plus 0.2 into 2 plus 0.15 into 3 plus 0.25 into 2 plus 0.25 into 2, which if you calculate is basically 0.45 plus of course 0.4 plus 0.45 plus 0.5 plus 0.5, and you can clearly see this is basically 1.4 plus 9, this is equal to 2.3 bits per symbol. That is your L bar for the Huffman code. This is the what we have just calculated is basically your average length. Okay, so this is the average length for the Huffman code. So this is the average length for the Huffman code. To see, remember, to see how close this is, the lower bound of any such code, not just the Huffman code, but for any prefix free code is given by the entropy. So to see how close it is to the lower bound, let us calculate the entropy, and the entropy is given as this is equal to two symbols with probability 0.15. So twice into 0.15 log to the base 2 1 by 0.15 plus 0.2, one symbol with probability 0.2 log to the base 2 1 over 0.2 plus twice into 0.25 into log to the base 2 1 over 0.25, which is equal to 2.2855. So this is the lower bound from the entropy, and you can see the Huffman code is tantalizingly close to this. If you can look at L bar minus Hx, that is equal to 2.3 minus 2.2855, which is equal to 0.0145. 0.0145 bits per symbol. So the Huffman code is only 0.0145 bits per symbol from the lower bound, which is given by the entropy. Okay. and therefore the Huffman code. So therefore this shows that even for this simple code, so this shows that the Huffman code is very efficient. It's only 0.014 or approximately 0.015 bits from per symbol from the lower but further you can reduce. Now remember, to approach this to become arbitrarily close to the lower bound, one has to code over larger and larger blocklets. All right. So by employing the Huffman code or this scheme for constructing the Huffman code over larger and larger block lengths, one can achieve an average code length which is arbitrarily close. So arbitrarily in the sense that is achieve an average code length which is as close to this lower bound, that is entropy, as desired. So by coding over larger and larger block lengths, achieve average code length that is arbitrarily close. Okay. Achieve average code length that is arbitrary. So by coding over larger and larger block lengths, one can achieve an average code length that is arbitrarily close to the lower bound, which is the entropy of the source. Okay. So basically in this module we have seen the Huffman code, which is an elegant and a very simple scheme to construct the optimal code, all right, and which is very close to the lower bound. That is, so we have illustrated this using an example, constructed an Huffman code, verified that it indeed gives a prefix free code. All right, we have seen the procedure in detail, and also we have seen that the average code length is fairly close to that given by the lower bound, that is the entropy, and one can further decrease the gap between the average code length and entropy by using this procedure, the Huffman code, over larger and larger blocks. That's as we have seen over the previous modules, that is, once you code over larger and larger block lengths, one can achieve an average code length that is as close to the lower bound as desired. Okay. So we will stop here and look at other aspects in the subsequent modules. Thank you very much.